Hello, everyone. My name is Justin Stark. I am a project manager here at Star Industries. Recently, our team has been tasked with designing a new headquarters building for the TechSmith software company that'll be located just south of Michigan State University's campus in East Lansing, Michigan. I really appreciate you all taking the time to tune into this presentation, and I'll now get started with a bit of background regarding the design team here at Star Industries. So, as mentioned before, my name is Justin Stark. I'm the project manager on the TechSmith headquarters project. Our structural specialist is John Thompson. Our pavement specialist is Parker LeGrau. Our transportation specialist is Nick Holly. Our hydrology specialist is Blaine Libby. And our two environmental specialists are Jack Stelly and Ryan Brown. A little bit of background of the existing site. It's about a 5-acre plot of land located at the intersection of South Harrison Road and Crescent Road in the vacant apartment neighborhood of Spartan Village. So Spartan Village is located just southwest of Michigan State University's campus, and this project will actually be the first recent development project in this area. So the four main goals that have been kept in mind throughout the design process of this project can be seen here. We plan to develop a new headquarters building for the TechSmith software company. While constructing the building, we will do everything in our power to minimize the impact of traffic flow in the surrounding areas. We also plan to use multiple means of green infrastructure, which will in turn help us to achieve our gold LEED rating at the end of the project. A set of design criteria has been outlined by TechSmith in terms of what they are looking to see in their new workplace. So they're looking for a 2-story, 62,500 square foot building that will comfortably accommodate and be the workspace of 300 plus employees. The parking lot for the building will include spaces for all these employees, as well as 6 electric vehicle charging ports. The building will also include 2 outdoor patios, one on the first floor and one on the second floor. It will include a variety of workspaces and PA systems. And in terms of green infrastructure, we plan to install a green roof as well as rooftop solar panels, a water retention pond, and 2 rain gardens. I will now pass it off to our transportation specialist, Nick, who will go over our proposed site layout.
Thanks, Justin. As he stated, my name is Nick, and I am the transportation specialist on the project. For the next couple of slides, I'm just going to talk about the overall layout of the site, some of the parking lot parameters, the access points on the site, and how the site will impact traffic in the area. Okay, so starting off with the overall layout of the site, we have our building facing west with a north to south alignment. This includes rain gardens as well as retention basins, which I will let our hydrology specialist get into later. But more on the parking lot. As you can see, our parking lot has 2 access points, one leading out to Harrison and the other leading out to Crescent. I'll get into later why these 2 access points are so important. As far as the parking lot goes, it consists of about 268 parking spots. 7 of those are handicap, with 2 van accessible. The parking lot is also fitted with electric charging stations to fit our green initiative. You may notice these boulevards here in the middle of the parking lot. These are ADA compliant and are there to keep pedestrians safe as they pass through the parking lot, for those who may have to walk a little bit further. We were provided that TechSmith will have about 300 employees, and seeing that it is a 62,500 square foot building, that requires a minimum of about 200 parking spots. So when designing the parking lot, I tried to fit that number in between 200 and 300, and that's where I got about 268. Because out of those, not everybody will be driving to work. Some may be taking a bus. So I fitted that percentage to be about 6% or 18 people taking the bus, as there is a bus stop located directly adjacent to the building, almost at the corner of Crescent and Harrison. South Crescent and Harrison, excuse me. Um, so yes, that brings us to about 18 people taking the bus. Um, that also leaves us with still about 3% of the employees maybe riding a bike, and this site is fitted with bike parking, so that works out. And about 2% will be walking, or 6 people. These numbers can be adjusted based on those who may be carpooling to work, or if not every employee shows up to work that day. In this slide, I will talk about the impact that building this site would have on traffic in the area. Aside from the site plan, my other job was to create a traffic impact study. This basically means collecting data on the surrounding intersections and seeing how, if the site being built would impact these intersections. This is done by using a formula to create a trip generation and plugging in these trip generation numbers into the said intersections and seeing how these will impact the level of service, vehicle delays, and queues of said intersections. I'll get into that more later, but for now, let's just focus on the surrounding intersections. First intersection would be North Crescent. This intersection is just north of the proposed site. It has northbound, eastbound, westbound, and southbound traffic, and it is a signalized intersection. The interesting about this intersection is that northbound traffic has no left turn, or the left turn is restricted, meaning that for those cars that want to turn left going northbound on Harrison, they must go through the intersection, take a Michigan left, head southbound, and then turn right. The other intersection of focus is the South Crescent intersection. This intersection is three-way traffic, having northbound, southbound, and eastbound. Eastbound has no through traffic as there is no road that goes past, so there's only left and right turning movements. This intersection is controlled by a stop sign for the eastbound traffic. Northbound and southbound are free to move. So, with this information, the CE 341 class went out and collected data on both of these intersections. With the data collected, I was able to create a peak hour for North Crescent. This peak hour was at about 7:45 a.m. to about 8:45 a.m. And the PM peak hour was from 4:45 to 5:45. They also collected data for the South Crescent intersection with an AM peak hour of about 8:30 to 9:30 and a PM peak hour of 4 to 5. With this information collected, I was able to calculate a peak hour factor, create my trip generations, and so on and so forth. Now with my AM and PM peak hour factors generated for both the North Crescent intersection and the South Crescent intersection, as well as the trip generations generated, I was able to divide the traffic impact study up into 4 phases. These phases include the no build phase of 2021, the future no build phase of 2041, the build phase of 2021, and the future build phase of 2041. What no build means in this case is the existing traffic data at the area if the site was never to be built. You take this and you compare it to the build phase of 2021 of if the site was to be built and how this will impact the traffic. This is done by taking those numbers generated by the trip generation and plugging them into the intersections. So for instance, numbers calculated were about 247 trips coming from north and 165 trips coming from the south. It's easy to identify them as north and south in this instance because Harrison contains both intersections of North and South Crescent. So with those trips being generated, you'll get different level of services, you'll get different vehicle delays, you get different vehicle queues. For level of service, you want a level of service of at least a D or higher for it to be considered a passing intersection. So based on the no build information, all intersections were working just fine and actually had an overall great level of service, as well as vehicle delays and queues were very minimal. With the introduction of the TechSmith headquarters, this happens to change. Because of the trip generations being so high for the South Crescent intersections, this intersection began to fail. However, this was fixed thanks to our site plan having not just one but two access points, one of those being on South Harrison. This South Harrison access point is left turn only, and because of this, it takes some of the stress that is placed on the South Crescent intersection and allows for the level of service to become a passing grade of about a D and allow for the intersection to work perfectly fine. Now, to get your future build phases and your future no build phases, you take your data that you were given and you apply a growth rate. So the growth rate that we were given was about 0.5% per year over 20 years. This gives you a number about 1.1049. Applying this in the next 20 years will have not a major reaction, but still an increase in the traffic volumes. Over the next 20 years, in both the no build phase and the future build phase, each intersection is still flowing perfectly fine. So, with the introduction of the TechSmith headquarters and the two access points that are proposed, our plan works perfectly fine and has no impact really on the traffic in the area.
Thank you, Nick. Now in the next slides, I'll be talking about the hydrological aspects for this design. As the hydrology specialist for Star Industries, the focus of my scope of work is centered around two goals: minimizing stormwater runoff that results from the new development site and maximizing water quality that does run off from this site. The Ingham County Drain Commissioner is the authoritative figure regarding hydrological development that upholds these values by implementing stringent standards and design criteria for all developments residing within boundaries of the county drain network. To meet these standards outlined in the code, the hydrology portion of the design is to include a wet basin retention pond, a combination of a bioswale network, culverts, and an enclosed pipe for stormwater conveyance, rain gardens and a green roof, and rain barrels to store semi-treated water to then be recycled as gray water. The proposed site layout pictured here consists of 22 separate subcatchments, 8 bioswales, a retention basin, 2 rain gardens, and a green roof, each with unique physical characteristics regarding area and runoff coefficient. The 2 rain gardens and green roof filter water from the building and subcatchments surrounding the gardens. These green features then drain into 4 rain barrels to later be pumped into the headquarters building for reuse as semi-treated gray water, either for flushing or irrigation for the landscaping on the property. There are 8 bioswales that drain stormwater from the subcatchments that don't drain into the rain gardens. 9 culverts assist these bioswales and are placed to convey stormwater under all paved surfaces. A single enclosed pipe carries water from the bioswales into the retention pond on the eastern edge of the development. Once the water reaches the retention pond, it stays there until it either infiltrates into the soil, evaporates into the air, or settles in the permanent pool where it will cycle through the pump that acts as an aesthetic water fountain for the development. The next step after deciding on a site layout was to calculate runoff using the rational method, resulting in a table as pictured here. In total, the area to be drained within the stormwater management system sums to 6.9 acres. While the development is only considered to be 5 acres, hydrologically speaking, water from higher elevations near the site boundary flows into the development and needs to be managed as well, accounting for the extra 1.9 acres of drainage area. As a result of the rational method, peak runoff flow rate from each catchment in units of cubic feet per second for different storm events was found using this framework in the table pictured here as a function of storm intensity in units of inches per hour. When doing these calculations, the Drain Commissioner's Code dictates that a time of concentration of 15 minutes be used for developments less than 10 acres. To determine volume, a modified version of the rational method was used where storm intensity was replaced with total rainfall in units of feet to end with a final volumetric answer in units of acre feet. Values of storm intensity were sourced from historical rainfall data for the site location compiled by the National Oceanic and Atmospheric Administration. The first element I'd like to analyze is the rain garden and rain barrel system. Pictured here is a sample cross-section of this system, and it's responsible for draining 9 subcatchments totaling 1.4 acres. This cross-section consists of 5 layers totaling 8 feet deep. Due to the grading of the bottom layer, each subsequent layer is graded as well. This is to promote directional flow of storm water through the rain garden. In the case of Rain Garden 1 that surrounds the perimeter of the headquarters building, the layers are graded in a way so that the water will collect above inlets which lead to the 4 rain barrels underground. For Rain Garden 2, the grading is done in a way so that the stormwater flows towards a culvert connecting to Rain Garden 1. The green roof will have a similar cross-section, with the only difference being the bottom layer will be an impervious surface and the grading is directed towards an outlet leading above the rain barrel inlets of Rain Garden 1. The 4 cylindrical barrels have a diameter of 20 feet and a depth of 14.3 feet, equating to a storage capacity of the volume runoff produced from the 100-year 24-hour storm for all subcatchments draining into them. This equates to a 1% chance of overflow, and in this case, an emergency spillway connects to the retention basin to prevent any ponding around the building. Next, 8 trapezoidal bioswales lined with native vegetation are responsible for conveying any stormwater not stored in the 4 rain barrels. In total, they drain runoff from 14 subcatchments totaling 4.15 acres. This is preferable to an enclosed drainage system as it promotes infiltration of stormwater along its path and partially filters out contaminants as well. Sizing calculations were made so the design could reliably convey peak flow from the 100-year, 15-minute storm. This equates to only a 1% chance of failure by operating outside of the design parameters. Manning's equation was used to size these elements along with a roughness coefficient of 0.035 as per the Drain Commissioner's Code, resulted in the area characteristics pictured here. Drain Commissioner's Code dictates side slope must be no less than 1 to 3 and grades must be at least 1%. Acceptable side slopes and grades are highlighted in green. Furthermore, no grade exceeds 2%, so check dams or drop structures were not needed. After area characteristics were determined, their path was contoured in a way so that any existing vegetation on the site would be undisturbed. To aid in efficient movement of stormwater, 9 culverts were placed to route water beneath all paved surfaces throughout the development. They are designed to be made of high-density polyethylene, HDPE, and a roughness coefficient of 0.011 was used in sizing calculations. Diameter was sized to the next largest U.S. standard pipe size using peak flow rate calculations from the 10-year, 15-minute storm and Manning's equation. Since stormwater is mostly conveyed through the bioswales around the development, there is only one pipe being used in the system. Stormwater from the 2 bioswales on the eastern edge of the development converge into a catch basin where the water then falls 3 feet below the surface and feeds into the enclosed pipe, which serves as an inlet to the retention basin. It is designed to be made of HDPE as well and has a roughness coefficient of 0.011. The 100-year, 15-minute storm and Manning's equation was used for the sizing calculations, given a minimum pipe diameter of 12 inches as outlined in the code, and thus equates to having a 10% chance of failure by operating outside design parameters, given the area characteristics in the table pictured here. The table pictured here compiles the results for peak water velocity through each hydrological element of the stormwater conveyance system given the area characteristics outlined in the previous slides. Values highlighted in green indicate a passing criteria set by the Drain Commissioner. For culverts, this criteria was set to be a maximum velocity of 8 feet per second for the 10-year storm. The highest value reaches 4.87 feet per second, passing the criteria. For the pipe inlet to the retention pond, this criteria was set to be a minimum velocity of 3 feet per second to avoid sediment, and maximum velocity of 10 feet per second when full for the 10-year storm. The velocity through this pipe is designed as 4.12 feet per second, passing the criteria. For the bioswale network, the criteria was set to be a minimum velocity of 2 feet per second to avoid sediment buildup, and a maximum velocity of 5 feet per second when full to avoid erosion for the 100-year storm. The minimum velocity for the network is designed at 2.19 feet per second from bioswale 8, and the maximum velocity reaches 3.0 feet per second from bioswale 4, passing all criteria for stormwater conveyance. Finally, once runoff reaches the end of the bioswale network and through the inlet pipe, it will settle in a wet basin retention pond with dimensional characteristics resembling an irregular trapezoidal frustum, as pictured here. Retention facilities are preferable to a detention pond as they result in zero outflow of runoff from the development site, satisfying the requirement to minimize runoff leaving the development and helping to preserve the integrity of local streams and rivers surrounding the area and drastically reducing erosion potential. The 5.8-foot deep basin has a storage capacity equivalent to the volume of runoff produced from 2 consecutive 100-year, 24-hour storm events. In addition to this storage, a permanent pool within the center of the basin extends 4 feet directly downward and is capable of storing a volume equivalent to 10% of the 100-year, 24-hour storm event. While unlikely, in case of overflow, an emergency spillway links to a county drain located on the eastern edge of the development nearest the pond. Since it was sized to hold 2 consecutive 100-year storm events in a row, the chance of overflow is only 0.01%. The basin's steepest side slope is 1 to 4.28 and is to be lined with native aquatic vegetation that acts as a buffer strip, satisfying all sizing requirements outlined by the Drain Commissioner's Code, including storage capacity requirements. For aesthetic purposes, a 1.5 kilowatt floating pump is situated in the center of the permanent pool designed to shoot water 19 feet into the air as it falls in a circular fashion around the jet with a radius of 10 feet, keeping all water contained within the pool. The pump is rated to function in water as shallow as 20 inches and is designed to rise and fall with the natural water level of the retention basin. This pump fulfills the role of providing leisure near outdoor green spaces for both employees and visitors. To break down the cost for the proposed hydrological design, the following elements are accounted for. Land excavation for water storage, which includes the retention pond and underground rain barrels, bioswales, and all grading. The length and size of all HDPE piping material used for culverts and pipes, the installation of green features such as rain gardens in the green roof, and the cost of the 1.5 kilowatt pump used as the water fountain. In total, the cost estimate amounts to $408,520 and ensures proper hydrological integrity of the development that either meets or exceeds standards set forth by the Ingham County Drain Commissioner. Next, Jack will give some background on structures for the building.
Thank you, Blaine, and hello, everyone. I'm John or Jack Thompson, the structural specialist for this project. In the following slides, I will be going over the structural design aspects of this project. The design criteria to be followed is set by the International Building Code 2015 and ASCE 710. Design was completed utilizing these codes as well as the AISC Steel Construction Manual. IBC 2015 gives regulations for design criteria such as building classification, building and floor heights, building area, additional strength and serviceability requirements of structural members, risk categories, snow loads, wind loads, and live loads. ASCE 710 sets regulations for load combinations used in LRFD strength design, base, strength, and serviceability requirements of structural members, and the process for determining the snow load on a flat roof. AISC Steel Construction Manual gives the design strength values of different shapes under compression, tension, flexure, and applied moments. It also gives the dead load values of any shapes to be used. Some of the structural goals, design goals to include efficient structural framing design, design of second floor deck and the roof deck, which was done using the Volcraft LRFD Steel Deck Manual, calculated sizing of beams, girders, and columns done in a cost-effective manner, design of a typical wind load resisting braced frame, and minimizing the estimated structural system cost. There are a number of constraints on the structural design to understand and account for. The first design constraint is the overall project budget. The overall project has an initial capital investment of $15 million. The cost of the structural components must be kept to a minimum so as to not go over budget when the other site development processes and features are implemented. Building and municipal codes are also a constraint. These control different features of the structure such as height, number of stories, and building footprint. Constructability is a third constraint which is important to this project, as it is scheduled to last no longer than 1 year. Designing the structural systems with constructability in mind means minimizing the probability of going over schedule as well as over budget. This was done throughout the design process by limiting the number of columns and therefore the number of structural connections. Limiting the number of connections is important as they can be difficult and take a significant amount of time and effort to complete. A fourth design constraint is the planned building layout. This is important. In order to achieve the architectural style and features that this building is planned to have, the structural design must account for some unique characteristics such as offset floors, relatively large ceiling to floor heights to allow for large windows which will provide lots of natural light throughout the building, a cantilever patio area on the second floor, large meeting rooms on the second floor, and cubicle space throughout the building. The final design constraint is the project location. In addition to restrictions set on the structural design by the International Building Code, being located on the MSU campus means that there are restrictions set by the MSU Campus Land Use Master Plan. These restrictions include the building being less than 8 stories high and having a site coverage less than 35%. The proposed structure adheres to both of these requirements as it is only 2 stories high with additional equipment located on the roof and has a site coverage of about 15%. For the structural framing, there is information to be gathered prior to laying out the structural framing. This includes planned internal space use, architectural features, and the planned building layout. The planned internal space use is important to the framing for the structure as there are large team rooms located on the second floor here, which should not be obstructed by the presence of columns within them. This is why there are no columns located at the intersection of line B with lines 3, 4, 5, 6, and 7 here. Shown below are the framing plans for the second floor and roof. One important note is that the cantilever second floor will likely result in beams, girders, and columns that are adjacent to line B being larger in size than others to deal with the larger applied moment and compressive forces acting on them, since there will not be columns spanning from the ground to the second floor along the outer edge of the structure along column line A from line 2 to 7. To complete the sizing of the structural members, the most important information that is needed are values for uniformly distributed live load, dead load of different structural members and components, snow load, dead load of the green roof and solar panels, and the dead load of the mechanical unit located on the roof. Following the Volcraft LRFD steel deck manual, the roof deck chosen is a triple span 1.5 BA36 acoustical dovetail roof deck made of grade 50 steel with a span length of 5 feet. For the second floor, the deck chosen is a 1.5 VLR 36 composite deck slab with lightweight concrete having a span length of 5 feet. The bay between lines 7 and 8 from line D to line E was designed as the typical second floor bay. This is because this bay will have the largest beam spans and therefore the beam design for it can be conservatively applied to the other bays. The second floor bay design was completed accounting for the second floor corridor design live load instead of the generic design live load for offices, as this causes more extreme loading. For the typical second floor bay, the following member sizes were chosen. The beams will have a 115 kip foot moment applied to them. so W10 by 49 with an available moment of 141 kip feet at an unbraced length of 32 feet was chosen. The girders will have a 595 kip foot moment applied to them, so W21 by 101 with an available moment of 597 kip foot at an unbraced length of 30 feet was chosen. The bay from line 8 to line 9 between lines C and D was chosen as the typical roof bay. This is because this bay will have to deal with some of the load of the mechanical unit located on the roof. This load, along with other loads applied to the roof, will result in the most extreme loading case on the beams. For the typical roof bay, the following member sizes were chosen. The roof beams will have a 200 kip foot moment applied to them, so W12 by 58 with an available moment of 225 kip foot at an unbraced length of 26 feet was chosen. The roof girders will have a 465 kip foot moment applied to them, so W18 by 97 with an available moment of 497 kip foot at an unbraced length of 30 feet was chosen. The columns will have a 265 kip compressive load acting on them. The shape chosen for the columns is W12 by 65, which has an available compressive strength of 348 kips and properties which will allow it to resist buckling. The design of a braced frame was completed choosing one of the planned locations for a braced frame defined by the architect. The designed brace frame is located along line 12 between lines C and D. The bracing system chosen was an X-brace, as these are most efficient in terms of handling loads relative to their cost. The brace frame was designed assuming only a windward load acting on the structure. The assumed value for the wind load was 10 pounds per square foot, and this brace frame has a tributary width of 90 feet with a floor-to-floor height of 14 feet. Design of the brace frame was completed using SAP 2000 for modeling and analysis. The shape for the bracing member chosen was an L 2.5 by 2.5 by 1/2 steel angle. This shape has an available strength and axial tension of 73 kips, which is controlled by the yielding limit state. This means the shape is certainly sufficient for handling the lateral loads caused by the wind, which will act on the structure. An estimated overall cost for the finished building with all interior and exterior finishing was calculated using a given unit cost value of $198 per square foot. This results in an estimated total cost for the finished building of about $12.5 million. Shown below is the cost estimate for the structural components and materials involved in this design. The disparity between the estimated cost of the structural components and materials and the estimated cost for the final building comes from many things such as HVAC, plumbing, and electrical systems, exterior facade, emergency systems like sprinklers, lighting, flooring, and other interior features. Now I will hand it off to Parker, who will discuss the pavement design for the development.
So, the main focus of the pavements portion of this project is an evaluation of the 3 roads surrounding the project site. These roads include South Harrison Road, Crescent Road, and Middleville Road. The first section of this memo describes the regulations on the roads, local, state, and federal, stuff like lane width, and how kind of the local, state, and federal, how they vary from each other or relate to each other. The next part is climate data, which provides us with a PG grade for the new roads that may possibly be implemented. The next part is the analysis of traffic demand, which occurs in easels, which helps with the later on portion of this report. There's analysis of the current pavement conditions, what kind of fractures they are, the PSI rating, the smoothness of the current road. and also subgrade characteristics based on the soil boring data in the area. So the second portion of this project provides 4 alternatives for renovations of the 3 roads. The first is a new flexible pavement option. That means taking out all the existing road and implementing a new flexible pavement. Similarly, there's a new rigid pavement option, and then there's also an overlay option, which includes just adding pavement to the top of the current roads, and then a mill and fill option, which is taking out a couple inches of road and putting in a new HMA layer on top. So then, after these 4 alternatives were provided, the thickness for each layer was calculated, cost analysis was done on each of these options for each of the roads, and that was to figure out what the most cost-efficient option will be. And then based on the current needs, which is more cost-efficient, the best option was chosen for our situation, and a capital cost was provided for this choice. So the first part of the first section of this report talks about the climate data in the East Lansing area. A site called LTTP Bind was used in order to find the binder grade for each of the roads. And since they're all in a similar area, they all will have the same binder grade. And that ended up being PG 58-22. So next, the traffic data was analyzed in terms of easels, and it showed that Harrison had the highest traffic count, followed by Crescent, and then finally Middleville. So then those will be used along with all these other things to calculate layer thicknesses at a later part in the report. Next, it gives kind of an overview of the current pavement conditions. There's a map provided so that you can look at the different sections of road, see what kind of existing fractures there are, what kind of fractures there are. And for the most part, they were all in good condition. Harrison had very little fractures, and if they did, they were filled. There were some more significant fractures on Crescent and Middleville, but I still wouldn't say that they were huge fractures that will be a problem in the near future. So the next is the analysis of the soil, which an MR value of 4,500 was found for all 3 roads. This was because of the limited soil boring data in the area, and it was assumed that there wasn't going to be too much variation between the subgrade soil in the 3 areas. The next part of the report covers first the thickness values that were found for each of the options for all 3 roads. Now for the flexible option, a value of 5 inches for the HMA depth was found, 5 inches for the base, and around 13 inches for the subgrade. Now this did vary a little bit depending on the road. Roads with higher easels may have a little thicker than 5.5 to 6, but they all ended up being in that general area. The rigid value was around 8 inches for all of these. Same kind of thing, it varied depending on the various factors of the roads. And an overlay option of 2 inches was found, and similarly a mill and fill of 2 inches was decided for the cost analysis. So after an LCAA analysis was run on all 3 roads, the new flexible and the new rigid pavements ended up being a lot more expensive than the other 2 options. And since the current roads are not in need of a full renovation, they don't need all the layers torn out and new ones to be put in, it was decided that these didn't need to be seriously considered. So the cheapest option ended up being the overlay option, but it came with the trouble of having to raise the curb and gutters to the new height of the road that would be on there. So instead of worrying about that, it was decided to go with the mill and fill option, which was still relatively cost efficient. It wasn't that much more expensive than the overlay option, but it still provides a new ride surface for the expected raise in traffic after the creation of the site. So, once a 2-inch mill and fill was decided upon for each of the 3 roads, next came deciding what type of pavement material should be used. I decided upon an HMA 5E3 mix. The E3 relates to the amount of easels that the road is expected to have, and the 5 is a good top layer. And obviously the top layer of pavement's the HMA layer. So next was calculating the capital cost. So the prices that are included in this capital cost are the material cost for that 2 inches of HMA 5E3, along with cold milling for each of the 3 roads. Now, the parking lot is also included in my capital cost analysis. So the parking lot design that I came up with was 2 inches of HMA 5E3, followed by 3 inches of HMA 4E3, and that makes up the top HMA layer of a total of 5 inches. Next is the base layer, and I decide upon a 6-inch aggregate base that is followed by a 6-inch subbase. Other aspects that were also taken into account when calculating this capital cost were curb and gutter for the entire parking lot and the excavation that it would take to remove the materials that are currently there. So, after all of these are added up together, also including traffic control for the construction that would be happening and a use cost, the total price came out to $800,073,183.
Hello everyone, my name is Jack Stelly. Myself and my colleague Ryan Brown constitute the environmental team here at Star Industries, and I'd like to begin this portion of the presentation with the goals of improvements to be made to the East Lansing Water Resource Recovery Facility. In light of the construction of TechSmith headquarters, it is deemed beneficial to improve the waste facility of the region in order to support development in years to come. The first primary upgrade is converting the East Lansing facility into an integrated fixed film activated sludge system in order to improve the efficiency of nitrogen and phosphorus removal. Second is incorporating an anaerobic digester, and this would be to aid in the extraction of carbon through the form of methane gas, while also providing an on-site source of energy production. Along with these upgrades, we present efficiency, regulatory, and financial findings, all to be further detailed in later slides. In contrast with conventional reactors, the IFAS system includes a free-floating medium which aids in the generation of biomass. This free-floating biomass provides additional surface area for reactions between that biomass and the wastewater influent in order to help that sludge settle out. This highly efficient supplemental surface area allows for increased capacity without increasing the size of the tank, which saves the producer both money and footprint if implemented. As for nutrient removal, the biofilm and floc produced in this IFAS system allow for enhanced phosphorus removal, and the improved nitrogen removal occurs due to the strong nitrifying population of the unit. The waste-activated sludge also provides an excellent means of organic material removal, minimizing that final effluent needing to be taken off-site to a landfill or other destination. Yes, this system is a bit more expensive than current alternatives. However, with the increased capacity, the facility would operate at a much higher efficiency, and the reduced mass of effluent to be transported will save a considerable amount of money through labor, fuel, and equipment. Moving on to the anaerobic digester, this unit has considerable potential to both aid in wastewater processing and produce energy on site. This unit is comprised of a temperature and pressure controlled system in which non-recycled waste activated sludge mentioned in the previous slide is broken down into methane gas. The reactions in order for this to occur are listed in this figure seen here, and further details can be found in the technical report of the environmental team. These digesters have the potential to significantly reduce energy costs. Our design, for example, achieved a self-sufficiency rate of 32%, meaning that about a third of the energy needed to run the facility could be generated by this anaerobic digester on site. During this process, the carbon is removed and the volume of the waste is minimized. This, again, mentioned in the previous slide, has potential to save money in the terms of final waste distribution. A final note to be added about the anaerobic digester is the exciting potential to include additional food waste from local food producers and possibly even restaurants. A program like this, if chosen to be implemented, would increase the revenue of the facility. It would also produce additional energy, while also helping mediate the issues of growing landfills and overflow pollution.
Now, moving on to our technical design for the upgraded East Lansing Water Resource Recovery Facility, we decided to create two separate designs in order to compare some parameters we needed to do more research about. Those parameters included which carbon compound was to be injected into the secondary treatment process, the inclusion of a thermal hydrolysis process before anaerobic digestion, which would expose the sludge to higher temperature and pressure, better preparing it for anaerobic digestion, and the inclusion of a final aeration tank during the tertiary treatment process. Besides those changes, however, the rest of the design was the same, including the new IFAS system we wish to install and the new anaerobic digester. When comparing the results of our two designs, the first thing to point out is the general similarities between each design. Each variable within the facility's effluent is roughly the same. The total phosphorus and nitrogen levels, as well as the pH of the water effluent, are very similar. With this, we can conclude that the methanol and volatile fatty acids, as the carbon injection during secondary treatment, seem to be similarly efficient in sludge removal. The only notable differences between these two technical designs is the oxygen levels in the effluent, as you can see in the table above. Technical Design 2 has a higher dissolved oxygen level and lower BOD level, meaning the final aeration tank added a significant amount of oxygen to the effluent. Again, however, these two designs are roughly the same. Now, further comparing our two technical designs, we have to keep in mind the EPA and state regulations we have to follow. And then, as you can see in the table on top, we have to keep our carbon levels under 7 milligrams per liter, our nitrogen levels under 1.5 milligrams per liter, our phosphorus levels under 1 milligram per liter, and our microbial pathogen levels under 200 milliliters per 100 milliliters of water. And all of these standards were monthly averages. And we also had to keep our water effluent within a 6.5 to 9 pH range, and this was a daily range given to us. And even with that in mind, both of our technical designs were still successful. And further on, as you can see in the lower table, our two technical designs had very similar nitrogen and phosphorus removal rates, which goes further to prove that methanol and volatile fatty acids were similarly efficient in that aspect. But then on a last note, when comparing these two designs, Technical Design 1 proved to generate more energy from the anaerobic digester, and that was because it included the thermal hydrolysis process, and Technical Design 2 proved to produce much less energy. With all the variables previously mentioned, we have come to a final decision. Star Industries recommends using a thermal hydrolysis process as it permits more energy in the anaerobic digestion, as shown earlier. We also recommend using methanol in the secondary treatment process because, as it was similarly efficient to volatile fatty acids, it is significantly more inexpensive, so simply on that note, we recommend methanol. We also recommend against the use of a final aeration tank in the tertiary treatment process, as the only purpose it served was adding oxygen to the water effluent, and that didn't prove to be useful in this case, as we were within regulations nonetheless. And further on, we still highly recommend the installation of an IFAS system as well as an anaerobic digester, because with current research it proves to be incredibly beneficial. And to finish off, we hope our research and recommendations were useful, and we thank you for this opportunity.
Thanks, guys. Here we can take a look at the general cost estimate breakdown for the construction of the new headquarters building. So as you can see, the majority of the construction cost comes from the actual building itself. After determining the project subtotal, we took 5% of that subtotal and added it back on to account for the design cost, which you can see there at the bottom of the table. Additionally, we took 10% of the subtotal and added it to cover any unexpected costs that may be encountered during construction. After doing these, we determined a grand total of just around $16 million for the total project construction. And here we have our preliminary construction schedule for the project. So the schedule was broken down into 2 phases. The first phase being the engineering design period. Since we wanted to have our schedule mimic that of the actual ongoing project, we decided to have phase 1 finish at the end of May 2021, which would then allow for the second phase to begin in early June of 2021, which is the construction period. Again, trying to mimic the schedule of the actual project, we began construction in early June of 2021, and we plan to finish construction in April of 2022. You can also see that a 90-day break from work was implemented in the schedule to account for the winter period in Michigan. And with that, I would like to thank you all so much for taking the time to listen to this presentation. We hope that you learned a thing or two about the project. I wish that there were a way to interact and take some questions right now, but unfortunately there's not. So I will wrap the presentation up by saying thank you, and I hope you all have a great day.